graphs in Desmos, not just because it's digital and it's easier and it's usually going to look better, but because Desmos is actually going to add some functionality that will be really, really useful to us as we progress throughout this year. So we're going to go through a few different things. You can see the list off there to the left. I created that list by hitting this add item and then writing notes. Okay, so those are just text files that Desmos does not try to graph or do any math with. It's just if you need to annotate something or what have you. I like to keep my equations organized and perhaps group them into categories. That's really, really useful. Expression is probably the main thing that you've done in the past. You maybe have added an image or a folder. I actually haven't messed with the folders. I don't really know what that's about. But the table, that's the first thing that we are going to work with, is adding a table. So that's our first goal here. It automatically populates it with X and Y. And then you can go about adding in the points. So I'm just going to do something super simple. All right. And you can see as I add that Y coordinate, Desmos begins to graph the data, which is fantastic. You can do fun things. If you just toggle this on and off, it will stop plotting the data. You can have multiple tables at once, so that can be handy. If you click it and hold it, a bunch of different options will show up. You can change the color, which is always enjoyable. You can change what the points actually look like. Again, if you're graphing multiple sets of data, this is going to be handy. You can add connecting lines, which we almost never do in chemistry. Don't do that. And then this is a cool feature. You can actually drag the data. You could pick a point and move it around, and the table rather would reflect those changes, which is pretty fantastic. So there's that, just that full translational movement, and then I believe this one, just you can change either so that would be changing the X component or just changing the Y component is the other option. Okay. So that's just some random data. I actually have a table all the way made up, which is why this says X2 and Y2, because I have an X1 and a Y1. So I'm going to get rid of this one. I'm going to go find this guy and drag him up. Okay, so this is the table that I'm going to work with and graph, and we will interpret this. So I'm going to turn on the data. You'll notice that it didn't show up. Where is it? Well, the X coordinates fit within the range that is on my screen, but the Y coordinates definitely do not. So that's one of the first things I'm going to have to change. Just for funsies, I'm going to change this to green because I really like green, and that's going to make me happy. You could add a Y2 and a Y3, etc. But for our purposes right now, we just need one set of data that all have the same X and Y coordinates. The next thing we need to do is label the axes. All right, this is really important in chemistry. It's not just X, Y coordinates. We have data that we're graphing, and we have an independent variable and a dependent variable. And before you even make your table, you should know which one is the independent variable and which one is the dependent variable. Your independent variable is going to go on your X axis. Your dependent will therefore go on the Y. Okay, so how to label your axes. This little menu right here, this is going to be your friend, the graph settings. If you go in here, you can actually add labels to the axes. So this data set that I have right here, I just happen to know that it is the speed of a car, all right, and it's broken down into time and distance. So time is almost always an independent variable. Very rarely is time going to be a dependent variable. So I would have time, right? And we talked about this in your notes. You need to have the label, but then you also need to have the unit. So this would be in hours. And then my y-axis is distance in miles. Okay, so the way we interpret this, after a half hour, this car has gone 49 miles. After a full hour, it's gone 115 miles, etc. Okay. Now that doesn't fix the being able to see the points yet, but now you can see that my axes are labeled. The one failing that I have not been able to rectify in Desmos is being able to put a table title right, or I'm sorry, just a title right on the graph. You can title it over here, which I will do. I will say this is going to be distance versus time, or you could say the impact or the effect of time on distance, etc. Whatever makes you happy. Okay. Again, that's actually a little side note that I have down here. Remember to add a title. After you export the graph, you're going to have to go back in and manually add it to the table itself, or the graph itself, rather. All right, so back to this. I've labeled my axes. I have my table. I know what my x and my y coordinates are. How to fit the axes to the data set. There's two options. You can go back into this menu, and you can mess with the axes. So for the x-axis information, let's see, I've got data ranging from about 0 to 5. Normally, if this were any other graph or like not Desmos, I'd say perfect, that's great. But if you make it just plain old 0 to 5, that's not my favorite, just because you end up losing, you can't see the actual x-axis here. So what I would do is say, I don't know, -2 to 5, for instance. All right, maybe -1. And then for my y component, all right, this ranges from about 50 to 500. Again, I want to be able to see my axis, so you don't have to start at 0. I'm going to make this -20, and then I'll go up to 500. And there you go. Now you can see your points. Okay. This looks like a pretty 1-to-1 ratio in terms of slope, but it's very much not. Notice each of these big squares on the y-axis is 100. Each of the big squares on the x-axis is just 1. So pay attention to your scale. All right, so that's how we label the axes, how to fit the axes to the data set. There's actually another trick for that. You can go in here and do what we just did. You can also control how big each little square is. So I could say that each little square is going to be 0.5 for my x-axis, right? That changes the grid pattern. Usually I just let it do its own thing unless I have another motive. But another way to do this, let's say that you don't like it, you zoom back in, I just hit that little home button there. If you go on the table and you hit this little zoom fit button, and you actually click it and not just say you clicked it, there we go. It will automatically zoom to something that's fairly attractive and useful. Okay, and then you can play with it from here a little bit. Like, I don't like all that space, so I'm gonna go like that. And I might just zoom in a little bit. So you can mess with it to your heart's content. Remember, we try and minimize white space because the white space doesn't tell us anything, especially in this instance. All right, so we have labeled axes. We have zoomed in appropriately. That's what this meant, right? It's just zoomed, not that kind of zoom. Gosh, we do that kind of zoom enough. How to create a line of best fit. So this is where I'm going to add an expression. When we're doing a line of best fit, our data looks very linear, so we are going to use y equals mx plus b, but we need to talk to Desmos in its language, okay? And what's awesome about Desmos is that it will, and your graphing calculator does this too, but this is nice because it's on the computer. It will take the data from the graph that you pre-programmed and use that to calculate a line of best fit. But we have to, again, speak to it in its own language. So it's not just x, but x1, and not just y, but y1. So I'm going to change y1 to, or I'm sorry, y to y1, and actually all I have to do is just have my cursor right next to y and hit 1. I'll do the same thing with x. Okay. M I'm going to leave behind, or alone rather. That just means slope. And then B is going to be your y-intercept. There are instances in which you could make your y-intercept 0 if you know that the line of best fit goes through the origin of the graph. We don't know that, so we're going to leave it at B and let Desmos figure it out. Now, I said this already, you got to speak to Desmos in its own language. You don't want to say y equals mx plus b. Instead, I'm going to pull up my keyboard. You need to use this little sign right here. It's called a tilde, instead of the equal sign. And it is on your keyboard as well. It's in the top left-hand corner. But I will just hit this. Instead of the equals button, we have to use that little tilde. And what that means, again, it's just Desmos language. It's saying like y1 is defined by mx1 plus b. Okay. And then look at that. I've got this line of best fit, and it's going to give me a lot of really awesome information about that line of best fit. For instance, the R-squared value tells me how closely it matches my data. And then it'll give me some other parameters as well. It'll tell me what my y-intercept is, if that's interesting information to me. But even better, it tells me what my slope is. Now, why do I care so much about the slope? I care so much about the slope because I'm going to make Desmos mad again, but that's okay. Slope equals rise over run, right? That's the Algebra 1 definition of slope. What that means is y2 minus y1 over x2 minus x1. Okay, we know that too. Now, if we look at our axes and we think about these in terms of, well, you think about it in terms of data, not just numbers, but data. What are we measuring on the y-axis? Well, my unit for the y-axis is miles, and my unit for the x-axis is hours. So if I find the slope, and by find the slope I mean if I let Desmos tell me the slope, which it did right here, okay, and then I remember what the units of my slope are, what that means is if I have a slope of 101.867, all right, now remember that that's rise over run, or my y-axis over my x-axis, change in y over change in x. That's 101.867 miles over 1 hour. And what's that? Well, that's a velocity. That's a speed. So what I just found out by graphing a line of best fit is the average speed of this car across this data set. So that's fantastic. I know we don't care about cars so much in chemistry, but whatever it is we are graphing, hint, hint, density, that will come into play. What else is fantastic about this is if I go back and I change my data, like let's say, all right, I've gone for driven for 3.5 hours, I've got 360 miles on my tank of gas, and then I'm puttering to a slot, and maybe I got to push my car. So I went another mile in the next half hour, and then I went another mile in the half hour after that, so 362. Notice that my points have changed, and my line of best fit has also very drastically changed. All right, so this will evolve as you change your data if you need to change your data. And luckily, the Control-Z undo button works, which is very handy. So that's that. This is the goal right here, to find the slope. For our purposes, the slope tells us something if you interpret it correctly, which means if you are thinking about units. Last but not least, we need to save this sucker. All right, so hit that save button, and then we're going to export it. So share your graph. There's lots of options here. You can print it off. You can grab a link. Usually we're going to export it, and then there's some options about how you want to format it. Frankly, I don't know what this whole thing down here means. Actually, you know what? Let's find out. Wow, that looks terrible. Don't do that. Absolutely do not do that. What in the world? Wait, what's the other one? Now I want to know. Oh, that's really cool. Braille mode. That's fantastic. Okay. Anyway, I like the medium square. You can play with the line thicknesses, whatever you like. Okay, you download it, you save it, you upload it to Canvas, or put it in your lab report or whatever. And then the last little thing that you need to know about is remembering to add a title. Because again, I haven't figured out how to do that in Desmos. And if someone figures that out for me, that would be fantastic.